Welcome back to Maths with Mrs. J. We're now at the interesting point where we're able to put together a lot of our knowledge about functions, inverse functions, relations, domain, range, trig functions, derivatives of trig functions, and derivatives of inverse functions. Sounds like a lot. I think it's kind of cool how everything comes together. That's part of the beauty of maths, that it all intertwines with one another and it all makes sense and makes beauty together. Obviously, if you need to go back and revise your original trig functions, your sine, y equals sine of x, y equals cos of x, y equals tan of x, and so forth, go and do that. If you need to revise how to find an inverse function and the properties of inverse functions, what happens to domains and ranges, etc., that's probably a good idea to do that now as well before we proceed. Now, just a little word to introduce you to our inverse trig functions before we start actually differentiating them. We know that our y equals sine of x and y equals cos of x both go infinitely, obviously, for any x value in the domain of the set of real numbers. So y equals sine of x, normally you're going to have this sort of pattern repeating itself infinitely in both directions. Cos is the same thing really, but it just starts at a different place. The vertical line test is going to work everywhere on both of those functions. They are therefore functions. However, if we want to get an inverse, what we need to realise is that the inverse relation will be this particular function reflected about the line y equals x. Now, the problem here is that if you reflect this about the line y equals x, you're going to get something that looks like that, and the vertical line test will fail for your inverse relation. Therefore, it's a relation and not a function. Another way of knowing whether the inverse of a function will be a function or just a relation, you do the horizontal line test on your original. Now, the horizontal line test on your original doesn't hold. Therefore, we know that if we do an inverse of sine of x or cos of x, we're not going to get a function if we just use our whole domain. Therefore, what we do is we restrict our domain. For y equals sine of x, we restrict between negative pi on 2 and pi on 2. So here I've drawn our y equals sine of x in green, all right? So when x is negative pi on 2, y is negative 1. When x is 0, y is 0, of course. When x is pi on 2, y is 1. That's our original function there. So we've restricted our domain. In this case, your vertical line test, of course, works. We know it works for all of y equals sine of x. So it's a function itself. Because the horizontal line test works, our inverse relation will in fact be a function. And of course, it will be the reflection of this line about the line y equals x. So in orange, I've drawn the inverse there. All right, so that is how we define an inverse sign. We need to restrict our domain. Just bear in mind as well that when we restrict our domain of y equals sine of x, we restrict it to x between negative pi on 2 and pi on 2. So the range of that function, of course, is between negative 1 and 1, as it always is anyway. Remember that when you have an inverse function, the domain of your original will become the range of your inverse function, and the range of your original will become the domain of your inverse. That is what has happened here. Just a little word about sine negative 1x. That does not mean sine of x raised to the power negative 1. Okay, that's why we have for y equals 1 over sine of x, we have a special word for that, and we call that cosec. All right, that is supposed to avoid some confusion there. There are two other ways you can talk about inverse sine. Some people call it R sine or even arc sine. The important thing to remember is they are all the same thing. They're all the inverse function of y equals sine of x, however, with a restricted domain. Now we do the same thing with cos of x. However, because of the nature of cos that it goes from here to here, from 0 to pi, in order to get our horizontal line test working. If we went from negative pi on 2 to pi on 2, we're going to get a problem because we're going to get that kind of scenario. Horizontal line test will fail. So what we do here is we have our original function, y equals cos of x in green, from x equals 0 up to pi. Of course, the y values go from -1 to 1, so that's our range. They swap over for the inverse function, and of course we go, the domain of the inverse will be -1 to 1, that's fine. The range will be from 0 to pi. As well, just like here, you can use r-cos or arc-cos. Either of those is fine as well. Just another little aside here, you may or may not have realised this, you might have been told by your teacher, when you do inverse sine or inverse cos or inverse tan on your calculator in radians, the value it gives you will always be between these values here, okay? Sometimes when we're not talking about this here, of course, in terms of our unit circle would be our first or fourth quadrants. If we're talking about a scenario where we've got a negative sign, but it's not in the fourth quadrant, we're actually in the third quadrant, we would need to adjust if we're solving an equation. Same thing with your cos. This really only talks about your first two quadrants because it's positive in your first quadrant and negative in your second quadrant. If you're talking about either of your other quadrants and solving an equation, you would need to adjust that calculator value or that value that you get by doing inverse cos to the appropriate quadrant of your unit circle. Okie doke. I'm going to go to our next page and have a look at tan and inverse tan. Now we know that our y equals tan of x function is obviously repeated every pi, and we have our vertical asymptotes at negative pi on 2, pi on 2, 3 pi on 2, 5 pi on 2, etc. Everywhere where on your unit circle you're touching the vertical axis. Because remember, tan is sine divided by cos. Cos is the x value, and the x value is 0 on that y-axis of your unit circle. So obviously, in order to have a function as our inverse, we only take one section of this tan of x graph, and the section we take is between negative pi on 2 and pi on 2. Again, when we get our reflection in our line y equals x, this is what we get for y equals inverse tan. Looks exactly the same, but it's a reflection in the line y equals x. Similar to over the page, our domain and range will swap. So our limited domain for our tan of x, if we're going to be taking the inverse of it, is between negative pi on 2 and pi on 2. That ensures that our inverse function will be a function and not just a relation. The range, of course, is the set of real numbers. It goes infinitely in both directions. When we do the inverse, they swap over. So your domain will be the set of real numbers, and your range will be between negative pi on 2 and pi on 2. Notice how over the page I included the pi on 2. I had the square brackets. That's because they could be included. Here, you can't actually have those values because they are on asymptotes. So that's why I've got the curved bracket to say right up until that point, but not including. And again, just to point out that people can use the term arctan or arctan. Okay, so that's just a quick introduction. We haven't done any examples yet or anything like that. Just a quick introduction to our inverse trigonometric functions. We're now going to, in our next few videos, start talking about some important properties of them and how to differentiate them and how to integrate them. So stay with us. If you like my videos, please subscribe.